Hello everyone and welcome to some reverse engineering. Today we're going to be looking at a program that is a return to libc vulnerability, and we're going to look at bypassing PIE and ASLR and a canary as well. It's important to note, I learned when I was doing this challenge that if you're running a executable locally and you get given a binary as well as a libc file, it's important that you patch it so you have the same executing behavior in libc that you do have on the remote machine. So this was new to me, and I recommend this program called PatchElf, where you say, hey, here's the .so I was given and the program I'm running, and it'll automatically patch it and spit out a patched file. Okay, so let's have a little look. So I got the patched binary here. And pretty much it says we're learning how to read and write to a file. Would you like to read or write? And then you pass it a number, like 3. You know, just a simple program, nothing too crazy. And we can have a look at some of the control flow. So here in Ghidra, nothing too crazy. You know, the welcome message, read, would you like to write, put it in the buffer. We can see the canary here, but that's not really too crazy. So we can see here that the vulnerability comes from this puts here. We know puts is dangerous. It doesn't do any read size checking, so you can do a buffer overflow. So it looks like we have to overflow this buffer, which is the scratch pad. But it's important here because first of all, there's no win function in this. So, and there's a canary. So we can't just smash the stack straight away. We have to try and leak the canary. So we can look at normal execution here of this process. So it's, we have this puts call. So say in this case, I've just filled it with a arbitrary amount of A's. So just an amount that doesn't trigger the buffer overflow just yet, just so we can look at the behavior. The buffer is at the base pointer minus the 0x70 address, and let's have a little examine there and poke around. So here is the buffer, this section here, and then we start to notice some interesting things here. So if we fill up our buffer just enough, then what we should get is a write. So if we fill up the buffer here and then we do the write that is in the function, so because it spits out what's currently in the buffer, if we put a buffer that's long enough, it ignores these zeros, so they're not treated as end of string, and then so we can write out a buffer as well as what here is actually, curiously, if we type canary, we can notice that this is the stack canary here. So by filling up the buffer and getting it to print, we have a leak. We can see some other things here. So this is the canary. There's some other variables here, but some interesting things on the stack that we might want to leak. So we can send a payload. Just looking at the solve script here, if we send a payload that's long enough bytes, we can overflow it and leak out the canary. So if we have the canary, it means we can start smashing the stack. So the question is next, what do we jump to, or where do we go to? If we're doing ROP, we might want to look for some gadgets. But the thing is, like I said, we have the PIE and ASLR. So we can't just go, hey, open up ROP gadget, have a look around, and you know, once we find all the gadgets, we can't just pluck them out, right? Because the gadgets are loaded into memory at different offsets because of ASLR. So we can't just pick out these gadgets and use them. We need some sort of leak. So if we go back to the executing process and have a look again, we notice that we can leak the canary, but we also have some other things in the stack that may be of interest. So let's explore those. So we can look here and say, hey, show me treat these as instructions. So what's after these? So we can see here that we actually get a pointer to the address of a section in libc. So we get point to here, and then we notice it's a certain offset from the start of libc. So we can not only leak the canary, but we can also leak an arbitrary place in libc. Additionally, if we have a look again, there's some other addresses here that may be of interest. So let's have a look at this one and do the same thing. So this is a address on the stack to main. So the plan for this is to we can repeatedly in the program executable, we can, only unless we give a malformed input, it'll keep asking us. So we can use this loop to keep overflowing, to building a bigger and bigger buffer to leak more data. So firstly, what we'd like to do is leak the canary, and then leak the libc address, and then leak main if we want to. And then so once we have we can have a look here. So if we go VM, if we look at the memory map, we can see here that libc is loaded at this address. So later on in the video, I'm going to show there's two ways we can do this. If you wanted to use the gadgets and find the offsets manually, or you can have pwntools do this part of the process. Alrighty, so let's take a look. We have built the program to go through and leak the canary, the libc arbitrary address, and that's all we need for now. So let's have a look at that in action. We can see here that we print out the canary and we print out the libc leak. So we can say, let's have a look at VM map, and we can see that we know that libc is at this address, it's there, but we need to figure out that address given the leak that we have. So if we say, hey, the libc leak is at this address, and we know that this symbol is at the base address plus this, then we can just take this leaked address minus the offset of where we got given, and that will give us the libc base address, and then we can start using gadgets from it. So what kind of gadgets do we need to do? We can go have a look, and we can actually just have pwntools build it out for us. So we say, hey, we're going to make a RUP. We're going to make a RUP chain. We're going to say, hey, call libc system, find out where system is, and pass it bin bash, and it'll execute that. It's important to note here that before we do make system calls, we have to make sure that the stack is aligned. So what we end up saying is we build enough payload with some initial padding, write the canary, so we have to make sure that that's preserved, a little more padding, and then we say put in a return just to make sure that the stack is aligned, and then we put our chain. So if we have a look, we can sort of follow what that does. So we've now just hit what would be the normal return statement, and we have another return in there, like I said, for that stack alignment. And then we can see here that we do the return, go next instruction, that pops it off the stack, and then we can say, all right, now on the stack we have the bin bash string memory address, and we have a pop into RDI, which, remember that on 64-bit we have to load arguments, the first argument into the RDI register. So we say pop that into there, so our first argument is ready to go, return from the gadget, which pops that off, and then we're going to call system. And then so if we just allow that to continue, we now have a shell at the top, so we can just do ls and execute like that. for me, I wanted to dig a little more under the hood and just try see if I could replicate this behavior by myself and manually build it, just to get a better understanding. So let's walk through that. Alright, so if we're gonna manually build the ROP payload ourselves, we're gonna have to find those addresses as the PIE and ASLR went enabled and use those to then do some calculations. So I went through, and you can just use grep inside ROP gadget, and all I wrote was look for in the libc.so just a simple return by itself, because remember we need that for stack alignment. And then we can have a look at the other gadgets. So the next one we need is the pop RDI to put into the register. We could search for that, and there's plenty to choose from, but like this one will do perfectly just fine. And then the last one is we need to find the system call if you're manually doing it. So let's find the offset of that, which is this value here. And the last thing we just need is the bin bash string. Remember, you can use the gadgets that are inside the libc.so, or you can use gadgets in main. It's up to you really. You can do either of those to do this exploit. So now that we have the 3 offsets, so these are all inside libc at base address, plus these offsets is where you'll find our gadgets. And then so we manually just leak the address that we know about. We do the leak address plus this amount ends us at the start of libc. I'll put a photo of the offset calculation so you can follow along with that. And then we say, all right, we know the libc base address, add the offsets for each of our gadgets, and then the payload just looks like this. So padding, canary, more padding, and then this is where the actual return address here is, which is just our payload, and we can build a shell. All right, so let's load up and try our manual one. So we have a breakpoint. Type something here. It attempts to do the leave. Let's load this so we can actually look. So leave, tear down the stack frame, and we're ready to start doing our payload. So here's the first return that we put in. And let's actually follow along and have a look here. So we can see that what we have was 29CD6, which was the offset from the base. And we can see here, that's what we got, 29CD6. And then let's follow that, next instruction. So pop RDI, and what are we popping in there? The address of this bin bash. So RDI is pointed to this currently. Next instruction, follow along. Boom. Execute. And now look, RDA contains the address of our bin bash string, and then now we execute system. Continue. And we got a detach process. So there we go, we got our shell. Alrighty, thank you very much.